Howdy class, welcome to the next installment of this handout on sets and counting. Uh, Today we're going to talk about the multiplication principle. And we're going to begin talking about the multiplication principle by looking at the different ways we can get from town A to town C, where you have to travel through town B. So here, in order to get to town C, you have to travel through town B, and you have three different routes. You have route 1, route 2, and route 3. Any one of those routes can get you to town B. It's kind of like going from here up to Houston, right? You got to travel through Victoria. There's multiple routes. You can get to Victoria, and then from Victoria to Houston. There's more than one way to get to Houston. And so from town B to town C, you've got route A and route B. So what are all the different routes we can take? Well, we got a map out here. So from town A to get to B, you can, of course, take route 1. And then you could go route either A or B. So your route here would be 1A, and this would be route 1B. And then you also have 2, and of course after that, A to B. So your routes could be 2A or 2B. Finally, route 3, A and B, and so this is route 3A and 3B. Alright, so all in all, that is 6 routes. So let's we're going to be looking at how to generalize this, so you don't have to do a decision tree like this every time, just to figure out the number of routes to take. And so we're going to look at the multiplication principle. So here we have m tasks that can each be done in a different number of ways. So task 1 we'll call T1, and we're going to say that can be performed in one number of ways. So if you have like a particular task, it can be done 5 ways. And if another task called task 2, then that can be performed in a number of ways as well. Like N1 is just the number of ways for task 1. N2 is the number of ways for task 2. And so on and so forth until you get to your final task M, where you have which can be done in NM ways. So how can you figure out the number of different ways a task can be done? Multiply all the different ways they can be done together. So note that in the previous example, we had 3 routes to town B, and then from town B to town C, there were 2 different routes. 6. This is the multiplication principle. Alright, so we're going to do a couple of examples. So here we just have a flipping of a simple coin. Quarter, peso, dime, nickel, whatever, doesn't matter. Right, 2 sides to a coin. And so if you flip it once, what are the number of outcomes? Well, it's either heads or tails. So that's 2. Now if you flip it twice, right, that could be, first one could be heads, then tails, and then it could be heads or tails, heads or tails. 4 different outcomes, right? So 2, and then 2 outcomes after that, 4. Alright, now for part C, we're doing it 3 times. So that would be another flip of the coin. And note that would be 3 times. So we have 2, 2, 2, which gets us 8. Right, and so if we do it another one, right, making it 4 times, right? That's another flip, right? So this top one, heads, 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 or heads, 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 tails, and so on, right? They each have one, right? That's going to be 2, 2, 2, 2, 4 times, which gets you 16, right? It's the multiplication principle. Alright, so next one, we got a combo lock with 5 slots. And this will be kind of a unique combo lock because slots 1, 2, and 3 have 5 possibilities. So here's our lock. And we've got 5 combinations here. And here. And same thing here. Okay, that's 5. And then slots 4 and 5 have 8 possibilities. Okay, ran out of space, but you get the idea. And then you have another one over here that also has 8. So we got 5, 5, 5, and 8 possibilities, right? So just different things to make the right combination. And so what are the total number of possible combinations? Well, you just multiply everything together, right? 5, 5, 5 for the first 3, and then 8 and 8 for the next 2. You multiply those together, and you will have a possibility of 8,000 combinations. All right. So that's that for that part. Next one, we're going to look at permutations, and I believe that's actually 6.5, not 6.4. But permutations, given a set of objects, a permutation is a distinct order of those objects. So, for instance, all the permutations of set A, ABC would be, well, you could have the set as it is, ABC. You could have ACB. You could have BAC, BCA, CAB, or CBA. All right, those are all the different permutations that you could do of those 3 letters. And you can see how you could do a decision tree like we did before. Right, just like we had before, A, B, C, and then after that it's, it could be B or C, then of course that would have to be C, then that one would be B, and this one would be A, C. Alright, and so that's another way to capture them. So, all the permutations possible are 6. Alright, we're using up all the letters. So, let's look up, for set B, all the different permutations. Of course, you can set the same decision tree. Right, A, B, C, D, and you note that this is going to start getting a little bit more crowded than before, so we need a different way to do this. So it's still the multiplication principle, but we're going to say 4 times 3, right, because each time you go down the line, right, you've got one less choice, right? Just up here you had 3, then you had 2 choices, and then you had 1, so each time you go down 1, and so you end up with this, 4 times 3 times 2 times 1. Multiply those together, you get 24. Now, this operation that we just looked at, that's got a particular name. That's called the factorial. So 4 with the exclamation point. So bad math joke warning. This is not an excited for, it is a factorial. So what is a factorial? Where n is any positive integer, right? We start off at n, so take 1 away, all the way down to 1. So if it's 5 factorial, it's 5 times 4 times 3 times 2 times 1. Also, 0 factorial is always equal to 1. So to find the number of permutations of a set with n objects r times, we're going to use this equation here. And what we mean by times is how many slots we're using up. So in the previous example, what are the permutations of b? So we'd use our equation, right, because we used all 4 slots. A, B, C, and D were all used every single time. And so this is 4 factorial over 4 minus 4 factorial, ending up with 4 factorial over 0 factorial. Remember, 0 factorial equals 1. And so you end up with just 4 factorial, which we found earlier was 24 combinations. So next example, same set, but now we're only going to use 2 at a time. What does that mean? That means we're looking at all the different combinations, AB, AC, AD, and then BA, and so on and so forth, right? We're only using 2 letters. What are all the different combinations we could use? So P of 4, 2 is how we'd set that up. And so again, this would be 4 factorial over 4 minus 2. Factorial that. You end up with this. Of course, 2 times 1 is just 2. And so this will end up being 4 times 3 times 2 times 1 over 2 times 1. Right, 2 and the 1 cancel, so you're just left with 4 times 3. And so the number of combinations in this case is 12. Alright, so now we're going to look at the permutations of indistinct objects. Basically, you've got a bunch of objects, and how many times can you do them? Where you've got the number of object 1 is n1, object of number of times we see object 2 is n2, so on and so forth. The number of permutations will be given here. What does all this mean? Well, let's look at the example of the different ways we can write the word espresso. So we note that NE, which is the number of times E shows up, is 2. Right here and here. And the number of times S shows up, we have 1 here and 2 more here, so it's a total of 3. And then we have the number of times P shows up will be 1. The number of times R shows up is 1, and the number of times that O shows up is also 1. So add all these together, N equals 8. So now we just use our expression here. And so we've got 8 factorial over 2 factorial, 3 factorial, 1 factorial, 1 factorial, and then 1 factorial, right? Accommodating everything. Of course, 1 factorial is 1, so these last 3 just kind of disappear, and you're left with 8 factorial over 2 times 3 factorial. And the way you can work this out is you can just start writing out 8 times 4 times 3 times, well actually it's 3 factorial, right, because you just keep going down, over 2 times 3 factorial, and you notice we have this really nice cancellation. And so this ends up being 16. Excuse me. 16 ways to rearrange the letters in espresso. And that is all for today.